Hello everybody, my name is Smarth and today we'll be looking at two filters, the endpoint moving average filter and the derivative filters in digital signal processing. We'll also be looking at what these filters do to ECG and PPG waveforms. So let's get started. The endpoint moving average filter is described by this difference equation. This difference equation is nothing but averages the last m values where m is the filter parameter, x of n is the input signal and y of n is the output signal. To find the transfer function of this system, we take the z transform on both sides, and on the left hand side we get y of z, and on the right hand side we get this by applying the time shifting property of the z transform. We can expand this summation like follows, and we can apply the summation of a GP formula, and we get this. The frequency response of a system can be found out by computing the discrete time Fourier transform of that system, but since we have already found the Z transform, it is trivial to find the frequency response by replacing Z by e raised to power j omega. This is because the projection of the Z plane on the unit circle centered at the origin gives us the frequency response also. So in this equation, I just replace z by e raised to power j omega and we get this. We can take e raised to power minus j omega m by 2 outside of the numerator and denominator. So we get this, and this can be seen as the sine of omega m by 2, and the denominator can be seen as the sine of omega by 2 if we multiply and divide by 2j and 2j. It is important to note that the omega in this equation is the normalized angular frequency, and its value varies from minus pi to pi, and after that it just repeats. So you can take any interval, you can take it from 0 to 2 pi, or you can take it from pi to 3 pi, but the omega is taken from minus pi to pi, and it is a continuous variable. Omega can also be replaced by 2 pi capital F of Fs, where Fs is the sampling frequency and capital F is the analog frequency. And we can plot, instead of plotting from minus pi to pi, we can plot it depending on the sampling frequency of that signal also. And this F, the small f, is also known as the analog frequency. And now we've got the frequency response of the system. We can find the magnitude by taking the mod, and taking the mod is easy. This term magnitude is 1 and the rest, and we get the rest of the terms here. So this is the magnitude. Plotting this magnitude on MATLAB and taking the value of m to be 10, we get this nice figure. As you can see, the graph is continuous, and we get a huge lobe at lower frequencies at 0, which peaks at 0. It is similar to a sync waveform. The poles and zeros of this system can be found out by the transfer function we found in here. And as you can see, the zeros of this transfer function can be found out by finding the roots of the numerator, and the poles can be found out by getting the roots of the denominator. And we equate the numerator equal to 0, and we get zm is equal to zm minus 1 is equal to 0, and we solve this, and as you can identify zm minus 1 equal to 0, these are the mth roots of unity, and we can further simplify this to get the actual roots. There will be m roots around the unit circle centered at the origin and equidistant from each other. But also note that since one of the roots is z equal to 1, and when we calculate the poles, we also get a pole at z equal to 1. So this common factor gets cancelled, and we get no zeros at z equal to 1. So ultimately we get m minus 1 roots at the unit circle equidistant from each other except at z equal to 1. And from the transfer function again we can see that it has z raised to power m minus 1 in the denominator, which says that there are m minus 1 concurrent poles at the origin, which we can see here. So we can summarize by writing it like this: the zero, we have m minus 1 zeros at these positions, and we have m minus 1 concurrent poles at z equal to 0. And now we've got the zeros and the poles, and we can easily plot them using MATLAB. And you can see that we have, for m equal to 10, we have 9 zeros on the unit circle, and we don't have a zero at z equal to 1, and we have 9 concurrent poles at the origin. Now we'll plot the magnitude and the phase responses for different values of m, and we can see the thing that is happening while we increase the value of m. So for m equal to 10 it looks like this, and for m equal to 25 it looks like this. And you can see there are many, the number of lobes have increased, and they have also they also steeply decline, but they are still periodic from minus pi to pi. For 50 moving average filter, you can see the same trend, and the same trend can be seen for a m equal to 100. and and as you can see that as the value of m increases, the width of the main lobe, which is at angular frequency equal to 0, that decreases, the width decreases. And now we'll see the pole zero plot for these cases for different values of m. For m is equal to 25, we got this plot. You can see that we have m minus poles which are equidistant from each other at the unit circle centered at the origin, except we don't have a 0 at z equal to 1, and we got the same number of poles, 24 concurrent poles at z equal to 0. For m is equal to 50, we have the same situation. We have 49 poles at the origin, and we have 49 equidistant zeros on the unit circle. Same thing from m equal to 100. Now what will happen if we apply this system to a PPG signal? As you can see in this plot, the topmost subplot is the original PPG signal that was recorded, and on applying the endpoint moving average filter for m is equal to 10, we get a much smoother waveform, and we don't have these small spikes that we see in the original signal. This is because when applying the endpoint averaging filter, the values in the spike which are higher than the higher get reduced, and the ones which are lower get amplified, so we get a smoother waveform than the original one. From m is equal to 105, you can see it's much more smoothened out than the m is equal to 10 case. For m is equal to 50 and m is equal to 100, the signal is so much smoothened out that it loses the characteristics of the original signal. We can see the same thing for the ECG waveform. The original ECG waveform has a decent amount of noise, and it has a number of small spikes. But on smoothing it with the endpoint moving average filter from m equal to 10, we get this. We get a better waveform which can be easily studied. The m For m is equal to 25 and 50 and 100, we get these awkward waveforms which lose the characteristics of the original one. So the value of m uh, should be carefully chosen. Next we'll see the derivative filters in digital signal processing, and the first order filter, which is of the causal nature, can be described by this function: y of n is equal to x of n minus x of n minus 1. And the second order filter is described by this one, and this is nothing but the difference of y of n of this first order filter. So this y of n can be calculated by taking y of n minus y of n minus 1 for this first order filter, and we get the second order filter. The central derivative filter is a derivative filter taking a gap of two uh, two samples. Uh, Here x of n is the input signal and y of n is the output signal. To find the transfer function of all these three orders of filters, for the first one we just get this using the time shifting property of the z transform. Divided by x of z on both sides, we get h of z 1 minus z raised to power minus 1, and this is z minus 1 divided by z. The second order filter, we have a similar situation, x of z 1 plus z raised to power minus 2, and we get this transfer function. You can see it's just the square of the first order filter. The central order filter, uh, we can get the transfer function in a similar manner, and we get this z square minus 1 2z square, and we can factor out the numerator, we get z minus 1 z plus 1. The frequency response can be found in a similar manner to the endpoint moving average filter by replacing z with a raised to power minus j e raised to power j omega, which is equivalent to taking the projection of the z transform on the unit circle centered at the origin. We get this for each of the filters. So we get 1 minus e raised to power minus j omega for the first filter, e raised to power minus 2 j omega and for the second order filter, and for the central order filter we get 0.5 1 minus e raised to power minus 2 j omega. And of course we can simplify them by taking like common terms and doing some simplifications. Again, I'll say here that omega here is the normalized angular frequency, and it varies from minus pi to pi, and it can be decomposed into 2 pi capital F by small by fs, which fs is the sampling frequency and capital F is the analog frequency. The magnitude and phase responses of all these three filters can be easily plotted using MATLAB. The first order filter which we saw had the frequency response as 1 minute as this. So the magnitude response is like this, and as you can see it amplifies the frequencies at the higher frequencies in the higher sides, and it does not amplify, and it on the other hand it alternates the frequencies in the lower side. The second order filter, the second order derivative filter does a similar job. It amplifies the higher frequencies and it attenuates the lower frequencies. The central derivative filter, however, also attenuates the lower frequencies, but it also attenuates the very high frequencies. It only amplifies, or it doesn't amplify, it relatively doesn't amplify the frequencies which are intermediately related in the signal. The poles and zeros of each of these filters can be easily found. For the first order filter, we got the transfer function as z minus 1 by z. So if we equate the numerator to 0, we get z equal to 1, which is the 0 of the transfer function. And for when we equate the denominator equal to 0, we get z equal to 0, which is the pole of the system. That's what's written here, and if you can see the plot, we get one pole at x equal to 0, z equal to 0, and we get 1 0 at z equal to 1. For the second filter, it was, if you remember, it was just the square of this first order filter, and we get two concurrent zeros at z equal to 1 and two concurrent poles at z equal to 0, like this. For the central order filter, we get two zeros at z equal to 1 and z equal to minus 1, and two concurrent poles at z equals 0. This was because when we wrote the transfer function, we could factor out the numerator at z minus 1 and z plus 1, and when we equate it to 0, we get z equal to 1 and z equal to minus 1. Now we'll test this system using the PPG and ECG waveforms. The PPG waveform is like this, and it contains a much amount of noise. When you apply the first order filter here, as you can see, it like visually the frequencies, the higher order frequencies have been retained, while the slower varying frequencies have not been retained, and that's what we expected when we saw the transfer the magnitude response of the filter. And the second order filter does the similar job as the first order filter, except that the frequencies that it retains are much smoother and not abrupt. The central derivative filter, however, only keeps the intermediate frequencies and does not and attenuates the lower and the very high frequencies in this signal. So it has less frequencies than the first order and second order filter output. For the ECG waveform, we have a ECG waveform like this, and when we apply the first order filter, as you can see, it looks like that the higher frequencies have been retained just as we expected, and so is the case for the second order filter. For the central derivative filter, the higher frequencies have been retained compared to the original signal, but the frequencies are lesser than the first order and second order uh, filter. This is because it only lets the intermediate higher frequencies to pass. The first and the second order derivative filters seen above eliminate low frequency components and emphasize the high frequency components. This can be inferred from the frequency response graph above that I just showed you. In the above graphs, it can be visually seen that the higher frequencies are more prominent in the first and second order filters. The central derivative filter also attenuates the low frequencies, but it also attenuates the very high frequencies. It keeps the intermediate frequencies to pass. And that is all. Thank you.